Welcome everybody to the webinar. My name is Daniel Asuba, and today I would like to talk about the spatio-temporal femtosecond pulse modeling using the optics design software VirtualLab. Today we will talk about several topics, so I would like to start with the ultrashort pulse modeling using a so-called field tracing concept. After that we will discuss important optical setups and examples. For example, we will see the pulse propagation through an homogeneous and dispersive media. We will discuss spatial focusing of an ultrashort pulse using an off-axis parabolic mirror as well as a lens. Furthermore, we will calculate the diffraction of an ultrashort pulse through a diffraction grating. This, for example, can be used for the simulation of pulse stretchers and compressors. In the end, we will discuss a very special optical component for the simulation or for the introduction of group delay dispersion, which is a Gerard-Tourneur interferometer. And in the end, I would like to show you the latest research results which have been generated by VirtualLab in cooperation with our friends from the University of Vienna. So let's start with the ultra-short pulse modeling by field tracing. So if we talk about ultra-short pulses, we mean pulses of a length of a femto or even an attosecond. And these pulses are of increasing importance in optical technology. And this also requires the theory and tools for modeling of such kind of systems to propagate ultrashort pulses and to shape ultrashort pulses. And our approach, how we do this kind of simulation, is we use a field tracing approach to propagate the pulses in combination with a ray tracing approach for the analysis of the optical path length. And this combination turns out to be very efficient for the modeling of spatio-temporal evolution of femtosecond and even attosecond pulses. So if we talk about optical modeling, we have typically the following basic task. We start with some kind of light source, and then we propagate the light which is emitted by the source through an optical system, and after that we would like to detect the light. So this, for example, can be a detector which is transforming the light signal into an electrical signal, but of course it can be also some material surface where we do some kind of light matter interaction if we, for example, do laser material processing. And there are mainly two questions we have to ask if you want to tackle current and future challenges in optical modeling and design. First of all, we have to think about the light representation, and second, we have to think about the propagation of the light through the optical system. If we talk about representation of light, we directly come to the question of source modeling. And in VirtualLab, we are using an electromagnetic field representation, and typically we define this electromagnetic field in a plane which is situated in free space. So that means in a homogeneous isotropic dielectric medium, for example, like air or water. Typically this plane, for example, can be the outcoupling mirror of your laser cavity, for example. And we completely can describe the electromagnetic field by two electric field components, the EX polarization component and the EY polarization. And the missing four components of the electromagnetic fields, they can be calculated on demand directly by Maxwell's equation, meaning that from the EX and EY component you can calculate also the magnetic field and the EZ component. That means that VirtualLab includes all of the six electromagnetic field components if they are required. So you are also able to calculate the electric field, the magnetic field, for example. So if we talk about an pulse, of course it's very important to think about the temporal properties of the electromagnetic field. And here we are mainly using a Fourier analysis. That means that in VirtualLab the pulses are represented in the frequency domain given here by this omega. And that means that you can describe a pulse by a set of fully coherent monochromatic stationary fields, which we also call harmonic fields. So here, for example, you can see the definition of a single harmonic field. And if you now look here, for example, in the inverse Fourier transformation, then you directly see, if you plug in this here in the integral, then you see that you end up directly by a sum of full coherent monochromatic fields, which you have to evaluate to get the pulse in the time domain. So that means that in field tracing, we propagate and formulate all techniques for monochromatic and harmonic fields, and ultrashort pulses now can be decomposed in a set of harmonic fields by a Fourier analysis. And this allows the specification of any vectorial pulse type. So I would like to show you in a first example how you can represent now really in VirtualLab your pulse and how you can display it, so what kind of options you have. So therefore I will open VirtualLab. This is the main window of VirtualLab, and we will go here to System and New Light Path Diagram. And this new light path diagram, or this light path diagram, represents really our optical table in our virtual laboratory. And here we can now place several optical components and several predefined optical sources on our table, and we can combine them nicely together and can build a very complex optical systems very easy. So for example, let's start with a Gaussian wave, and this Gaussian wave means that the spatial distribution has a kind of Gaussian shape, or the lateral distribution is Gaussian, and we also have to think about the distribution in time. And therefore, I can go here to Source, Spectrum Generator, Pulse Spectra, and then here you can find plenty of different spectrum generators. For example, you can use a programmable spectrum generator. There you can program your own very complex spectral distributions representing your pulse. I will do it now very simple. I will just take a Gaussian pulse spectrum with a pulse duration of 10 femtoseconds and a carrier wavelength of 800 nanometer. And if you click here OK, then you will see here the spectrum of the pulse, or representing the pulse. If we now double click here on the source, we can go here to spectral parameters, and we can load in this spectral diagram. So now we have really loaded in all of the spectral components, and there are different amplitude weights. So now we can press OK here, and now we will add directly in front of the source, we will add two very important detectors for femtosecond pulse modeling, which is the virtual screen and the pulse evaluation detector. Now we can also connect these two detectors to the source, something like that, and now we can specify what we would like really to evaluate by our detectors. So we can here go in the edit dialog of the pulse evaluation, and we would like to see a 1D evaluation. We would like to calculate the full width of half maximum of the pulse length, and we would like to see the 2D evaluation. What 2D and 1D evaluation means, I will explain you in 1 second directly on this example. So we just now click here on OK, and we now start the simulation, and now we will get several results. So let's do it step by step. Let's start with the result of the virtual screen. So the virtual screen really is just calculating the harmonic fields in the plane. So you see here the x-axis and the y-axis. So you see here the spatial distribution of the pulse, and you can see here a single spectral component. So you see, for example, this spectral component of 663 nanometer has this amplitude distribution and this constant phase. You also could calculate the amplitude. And now we can also scan here through the different spectral components, and always the wavelength is changing here. And you also see that the amplitude is scaling because we are moving here towards the central wavelength. So if you now would like to calculate the temporal properties of this pulse, for example, directly in the center, we can do an 1D pulse evaluation, and then you would end up with this temporal distribution, which is just valid now really in the center of the pulse. Furthermore, what we could do is we could take here a line, and we could evaluate along this line the temporal properties of the pulse. In this case, we would end up with the following. We would have here the line again, and here on the x-axis we would have the time scale. That means that here you can really see now an pulse property, or the pulse properties or the time properties along the line we have specified here in our virtual screen. I mentioned that we are doing a full vectorial analysis. That means that you also can calculate the EZ component. If you just click here on EZ, you see here the spatial distribution, and you also could do the same here. Just select the EZ component, and you could start now the simulation again, and you will end up now with the EZ component here, and with the spatio-temporal properties of the pulse. We also can do really a 3D analysis, meaning X direction, Y direction, and time. In this case, we can generate a video. So, for example, I will make now a video of the X component. So I go here to Pulse 3D Evaluation and click here on OK. And I start the simulation again. And now I will end up with some special data array. So we have here again just several harmonic fields inside. And we can now load this harmonic field set. We can convert this into a video. This will just take a few seconds till it's converted. So here you see now I can go here to conversion and create bitmap sequence, and now we will end up in a few seconds with a video. I can also change here now the frame rate, how fast the video is played, and now I can really see that the how the pulse is arriving and disappearing in the time. So the video running means the time dimension, and you have here the x-axis and the y-axis in the window displayed. So you see that you have plenty of different possibilities how you can display and evaluate optical pulses in VirtualLab. So the representation by electromagnetic fields has not only an advantage for the source modeling, but it also gives you a great advantage for the light detection. because a light representation of electromagnetic fields guarantees the access to all physical quantities. So you can calculate from the electromagnetic field the intensity and the wavefront, but you also can calculate the polarization, the pulse duration, the chirp. Aberration effects are included. You can simulate point spread functions and MTF, and also classical beam parameter like M squared, divergence angles. But you also can customize your own merit functions. That means that if you have a very complex optical setup and you would like to optimize that, you can define your own merit functions using C# or MATLAB programming language, which helps you then by local optimization to improve the quality of your optical setup. So that means that in VirtualLab or by field tracing, we start with a set of harmonic fields and we have to end up with a set of harmonic fields. So now there's the question how we can propagate this set of harmonic fields through an optical system. Because up to now we just have considered the pulse in the source plane, for example here at z equal to 0, and we said, okay, we specify our pulse in frequency domain, and by an inverse Fourier transformation we get the pulse in the time domain. Here, by the way, the L represents the EX and EY component of the electromagnetic field. So again, it's full vectorial. So in another plane, not equal to z, we obtain the pulse in the time domain, obviously, again by an inverse Fourier transformation, but in this case we have to know the spectral components in this plane. This means that we have to propagate each harmonic field independently from the initial plane to the target plane. And mathematically, you also can write this by an operator equation. So you have to apply an operator S on the initial field to get the light distribution in the target plane. And if you now look, for example, in standard textbooks, then you will find, for example, for the propagation of a plane wave through isotopic, dispersive, and homogeneous media, the following formula. So plane wave means that we don't have the dependency on space, and we just have to multiply a phase term, which is just the wave number times z. And you can also now do a Taylor expansion of this beta, and if you do so, then you end up with the classical quantities like group velocity and group velocity dispersion, and also higher orders. So now what happens, how can we describe now a more general propagation operator? So for example, what happens if you have a pulse which has a spatial distribution which is not a plane wave? Or what can you do if you have a pulse propagation, or if you would like to simulate the pulse propagation for a complex optical system and not only in free space? So if we can answer this question, we can calculate the spectral components in the plane of interest, and by an inverse Fourier transformation get consequently the pulse in the time domain, including the group velocity, the diffraction effects, the group velocity dispersion, interference, higher order dispersion effects, and polarization. So let's start with pulses which have non-plane wave spatial light distributions. So here you have plenty of different opportunities how you can define such transversal beam shapes. So for example, you have already seen that we have plenty of predefined optical different sources, and kind of source catalog we provide. For example, here's some kind of higher order Gaussian beam or some kind of Straker wave. But you also can import measured mode profiles, as you can see them here, for example. And you also can customize your transversal beam shapes using a programmable source. So again, here you can use MATLAB or C# to describe the transversal shape of your beam. So I would like to show you in a second example how a Gaussian beam now can be really propagated through an homogeneous dispersive medium. So, and therefore we just slightly have to adapt our initial setup. So I will close all of the windows beside of our light path diagram we had here. So I will remove now the virtual screen. And now I will define the distance between the Gaussian wave and the pulse detector. And in this case, we would like to propagate the light over a distance of 20 millimeter. And currently, the material between the source and the detector is air, so it's really low dispersive. And that's why I will replace this by a more dispersive material, so I will place some glass. So I will go here now in the glass catalog. For example, here you can find the shot glass catalog, and then I will choose here, for example, BK7, and here you can see the dispersion and absorption curve of this specific glass. And now there comes also the question, how does now our propagation operator S looks like? And typically it's just a free space propagation technique, and VirtualLab provides an automatic propagation operator. That means that the user doesn't have to care about the propagation technique, and VirtualLab is using the best operator for you. However, to make things a little bit fast now, I will choose manually the Fresnel propagation operator, which is fine for partial fields. So the automatic operator in the end also would end up with the Fresnel propagation operator. However, it would take VirtualLab several additional seconds to decide which operator I should use, and this time I would like to store and directly choose manually the option we are interested in. So now I can again do in 1D and then 2D evaluation of the pulse, and I also would like to calculate the full width of half maximum of the pulse. So please remember, our initial pulse had a length of 10 femtoseconds, and now I do the simulation again. And now you will see that the pulse length has dramatically extended, so the pulse was stretched. So now we have 241.33 femtoseconds, which you can see here in the detector result line here in the lower part. And you can also again see here the pulse, the envelope of the pulse, and we also could now do, for example, see really the high oscillation, so we can really now multiply the carrier frequency and not only watch the envelope, and then you see how the pulse is really oscillating in time. And we also could do this again in 2D, so along a line, and here you see it in time, and the pulse is really now stretched. So now we have seen how we can propagate non-plane wave light distributions in VirtualLab, and now there comes the question how we can propagate now really ultrashort pulses through more complex optical systems. And if we talk about more complex optical systems, first of all, we have to think about what kind of optical systems we are interested in. And nowadays, you can find a huge variety of different types of optical systems, and this different optical systems in general can be described by a sequence of optical interfaces and subsequent media in between. So, and mainly the question now comes, the interfaces are mainly the interesting part. So nowadays people are interested in the simulation of smooth freeform surfaces. For example, you can see here an aspherical lens surface, or you can see here some cylindrical lens. Also, VirtualLab could simulate microstructured surfaces like some kind of sinusoidal grating, some kind of blazed grating we have here, but also some kind of microlens arrays, or you can also simulate some axicon arrays, for example. Furthermore, VirtualLab can simulate some kind of nanostructure. For example, here you see some nanopillar array, which, for example, can be used as an anti-reflection structure. Also, multi-level surfaces are very interesting. A classical example here are, for example, some kind of diffractive optical elements or some kind of computer-generated holograms, as you can see them here. Also here, VirtualLab gives you the great possibility to define and import plenty of different optical surfaces and materials. So, for example, we have again here several catalogs. We have an interface catalog, a stack catalog, and a component catalog where you can import predefined optical components. Also, again, we have here the possibility to program your own height profiles, for example, by some kind of analytical formula. You can also import measured or sampled height profiles, and if you are a user of Zemax, you also can import Zemax setups directly in VirtualLab. So I would like to show you now in a second example how fast and easy you can set up an aspherical lens which can be used for the pulse focusing. So therefore I'll go back again in VirtualLab and I close all of the windows and clear all of the detector results and start with a new light path diagram. And again I will use a Gaussian source. And I will specify the diameter of this Gaussian source, and it should have a diameter of 4 millimeters. So the waist radius laterally should be 2 millimeter, and I also have to specify my pulse spectra. This time I would like to have a pulse with a length of 5 femtoseconds. So I load in again here the distribution in the source, and now I have to specify my aspherical lens, which should be used for focusing of the pulse. So the asphere has the following parameter. So it consists of two surfaces, surface 1 with the radius of 2.75 millimeter and several aspherical constants, and the same you have here for surface 2. And we have a central thickness of 3.15 millimeter, and it's made of a glass from Corning. So we will build up this setup or this lens using an optical interface sequence where you can really define a sequence of surfaces and subsequent media in between. We can easily do this right now. So we double click here on the optical interface sequence, and now by drag and drop you can add here sequentially the optical interfaces and define here the distances. I will not do this right now because this would take some time to specify all of the parameters. I will just go here in our component catalog, and I have already prepared the aspherical lens, so we can directly see here now the two aspherical surfaces. And if you now click here OK, we have here the two aspherical surfaces in the optical interface sequence, and in between we have some glass, and if you go here on Edit, you see the dispersion curves of this glass. So now we press here OK to confirm the setting. And now we would like to propagate the light in the focal region. And in the focal region we would like to place two detectors. And it's always nice if you have two or more detectors, that before you do that you always add here some kind of dummy operator which is called an identity operator, so it has not really an optical function. It just helps you to specify the position of the detectors, because we will now place here 2 detectors, and now we can connect everything, and now we can connect both of the detectors. We can connect to the identity operator, which can be also called the focal plane, and now we just have to edit here 1 distance after the optical interface sequence, and not 2 distances, which we would have to do if you would directly connect the virtual screen with the optical interface sequence. So I will just edit here now the distance to go into the focus of the aspherical lens, and it has a focal length of 1.7671 millimeter. So now we can also go here in the 3D view, so we can nicely see our setup. We have a source which is directly in front of the lens, and we have a certain distance, and then we come up with the focal plane where we have 2 detectors. So now we just have to edit the pulse evaluation detector again. So we would like to get the EX component and also the EZ component, because you might guess that for an high NA lens, so this numerical aperture of this lens is 0.68, you will have also an EZ component. And I would like to get the pulse shape directly in the center position, and I would like to make a 2D evaluation. So I will do it along a line which is along the x-axis, starting from -30 micron to 30 micron, and I press here. I also set this here to 0, and let's keep this on. I will come to that later. Now we press here OK. And now we have already finished the setup of our optical system. So you see it's pretty easy and fast how you can build up such kind of optical systems. Now, during I explain you how VirtualLab is really propagating the light in the focal plane, during that time I will already start the simulation, because it will take some minutes. So I will just now again choose a propagation operator so that we accelerate a little bit the problem instead of using the automatic problem. And I will now just start the simulation, and during that time now I really will explain you what is VirtualLab doing during the simulations. So we stopped with the idea that nowadays we have an enormous variety of different types of optical surfaces, covering also a huge range of different structure sizes, going from the nanometer to the meter region. And we also have already defined that our light has to be represented by electromagnetic fields, because this gives us flexibility in the source modeling and the detector modeling. But now, of course, we also have to propagate these electromagnetic fields. And now there's a question, is there a modeling technique to simulate all of these different optical components, and this even in an electromagnetic manner? And the answer is no, there's not a single simulation technique, but we also don't need a single simulation technique. The concept of field tracing, or its main idea, is that the optical system is subdivided in several, or is divided in several subdomains. And in each domain, we use a different simulation technique to propagate the light. So that would mean, for example, here in the first part of the system, we could use, for example, a free space propagation technique to propagate the light from the source to the front of the microlens. Then we use a different simulation technique to propagate the light through the microlens. After that, we use again a free space propagation technique. Then we use a technique to go through the first interface here of this microscopic lens, go out of the lens, and then again a free space technique. So mathematically, this means that you can write your optical system not by only a single operator, but we use a sequence of different operators describing the light propagation in the subdomain. And here you see some examples what kind of simulation technique could be used. So for example, if we have here as a first component a lens, we for example could use a geometrical optics operator, but we are not using a classical ray tracing operator, but we really apply the geometrical optics laws on electromagnetic fields. Then in the second step, we take a free space propagation technique, which is full vectorial and has it's a rigorous solution of Maxwell's equation, including all the diffraction effects. And a third component might be, for example, some scatterer or some kind of diffractive optical element. There, for example, we could use the thin element approximation to propagate light through. And here maybe as a last component, there might be, for example, some kind of grating. And in this case, we could use some Fourier modal method, which is a rigorous Maxwell solver, and to propagate the light through the grating. So here again, you see some of the optical simulation techniques we have included in VirtualLab, and the clever combination of this different simulation techniques in different parts of the system we also call unified optical modeling. So that means that field tracing for pulse modeling is the pulse representation by a set of harmonic fields, and the pulse propagation by a combination of rigorous and approximated solutions of Maxwell equations in different regions of the system. So I will directly come back to the example we discussed before, but before we do so, I will just talk a little bit about the numerical effort, because the sampling of the pulse in the frequency domain is really the critical part in our technique. That means that this sampling in the frequency domain really gives you the number of harmonic fields which must be propagated separately through the optical system. And now there's the questions, how many harmonic fields N do we need? And so let's assume that we have an ultra-short pulse at the source, which is a bandwidth limited pulse with a pulse length of delta t. And the pulse has a bandwidth then, obviously, of delta omega. And this is inverse related to the pulse length times an coefficient alpha. And this coefficient alpha now depends on how you define the bandwidth and pulse length. So is it full width of half maximum, or is it 1 over e squared? So there are several definitions. You also know maybe from Fourier theory that the sampling distance in the frequency domain, so the small delta omega, is also inverse related to the time or to the pulse length. Now if you divide the large delta omega divided by the small delta omega, this gives you the number of sampling points or the number of harmonic fields which have to be propagated through the system. And then you see that the pulse length is cancelling out and there's just the alpha remaining. That means that from bandwidth limited pulse, the number of harmonic fields which are required to sample the pulse very well is independent to the pulse length. So that means if you take a 1 picosecond pulse, you will approximately need 10 or 11 harmonic fields. And if you take a 10 femtosecond pulse, you also will just need 11 harmonic fields. So here again also you can see, for example, the example of 3 femtosecond pulse and a 10 femtosecond pulse. You can see here the envelope functions, and you can see here the pulse with the carrier frequency. So you can really see the oscillation of the electromagnetic field. But for both cases, you just need 11 harmonic fields. But this is just true, obviously, for a bandwidth limited pulse. And now the challenging task is, okay, what happens if the pulse experience desired or undesired changes. So for example, desired changes might be a stretcher or a compressor, and undesired changes might be due to material or angular dispersion. So for example, if you take a 10 femtosecond pulse at a carrier frequency of 800 nanometer, this will result in a pulse with more than one picosecond pulse length after it has propagated through 10 centimeter of BK7 glass. So, and due to the fact that the sampling has to be invariant in the frequency domain, this extension of the pulse would require an 100 times finer sampling to avoid the aliasing in the time domain. So this also means that without a smarter handling of this effect, the modeling would require a set of about 1000 harmonic fields instead of 10 fields just to simulate the light propagation through 10 centimeter of BK7. So here again you see a typical example how the pulse is really stretching. Here in the upper row you see the pulse propagation through air around along a distance of 50 millimeter, and in the lower row you see the same pulse which is propagated in glass, and you clearly see that due to the dispersion the pulse is stretched. So that means that we have to find a solution how we can really avoid this dramatic increase of number of harmonic fields. And we have solved this using a smart and separate handling of the dispersion effects. And we have done this in the way that you can write, it's not an approximation, you can just write the initial spectrum by a residual field times a phase function. And this phase function is mainly determined by the optical path length, which is dependent on the frequency. And we have here a residual pulse, which also obviously has a residual phase. And it turns out that material and angular dispersion results in a strong but very smooth variation of the optical path lengths for the different frequencies. So that means that this can be simulated by ray tracing to reduce the sampling effort. And this now is really the main idea, that we just have to care in field tracing about the proper propagation and sampling of the residual field, and this is not really affected very strong by the dispersion, and so therefore there's not a significant stretch during the propagation. And the inclusion of the optical path lengths we do by a ray tracing analysis, and if we combine this now with the residual pulse, we have a very efficient pulse propagation technique, and this is implemented and used in VirtualLab technology. So if we come back to our 10 femtosecond example, which is propagating through the 10 centimeter BK7, it would mean that if you don't do the smart dispersion handling and keep the number of harmonic fields constant, you will observe classical aliasing effects like this, so you cannot really get the information to calculate the pulse length. If you now do a ray tracing analysis, you can see you get a phase shift for the different frequencies, and then you can do the smart dispersion handling, and then you can keep the number of harmonic fields constant and use just 11 fields instead of 1000 fields, and you end up with a very well sampled field in the time domain in the target plane. So that means that field tracing is not only the representation by harmonic fields and the pulse propagation by rigorous or approximated solutions of Maxwell's equations, but it also includes the ray tracing for the optical path length analysis to reduce dramatically the numerical effort we have. So let's come back to our pulse focusing example. So it's now finished. So it took approximately 5 minutes to calculate. So here you see the result of the virtual screen. You can see how each of the harmonic fields are look like in the focal plane. So you see that all of them are more or less confined in a very small region around the central point, and you see also that this setup is really perfectly working for a for the wavelength which is close to the central wavelength. And now we can also see here the pulse and the pulse deformation in the center of the beam. And you can also now go here to the envelope and convert it to the carrier frequency, and then you see here now these higher order dispersion and this chirp effects here. We can also now watch this in 2D. So we again are going along a line along the x-axis, and what we could do now is, for example, if we are interested now in the pulse properties or in the time properties of this pulse, not on axis but slightly on another axis, then we could extract this information. So all of these horizontal lines, which are perfectly horizontal to the parallel to the x-axis, this represents just the time shape on a specific position. So for example, we can now extract here the an off-axis point, and we can, if we do so, then we see now that here, if we are in the outer region of the pulse, laterally spoken, then the temporal properties of the pulse not really look like nice anymore, so it's already pretty ugly. And if you compare it to the initial one, so it has completely different temporal properties. So this is what we mean with spatio-temporal simulation, so that at each position x and y you really have a completely different properties in time. And also, I mentioned that the EZ component might be very strong, so you can also see here that you have here a nice EZ component, which is, if you compare it to the x-axis, it is pretty large. So we also can see it here in the Gaussian spectrum. Yes, so we can also see it here. So if you go here in the focal region, you can calculate also the EZ component here, and then you see here you have 744 maximum amplitude, and the EX component is just 3000. So 1/4 or 1/5 of the pulse energy is going in EZ direction. So I hope you see that this field tracing approach really gives you the great flexibility for the optical modeling and design of your optical systems. Because in principle, you can simulate any kind of source model. You can include any kind of modeling technique, and you can include any kind of detector function. So why I say any? Because it's really, you can really include any of them. Some of them are provided by VirtualLab, some of the simulation techniques and source models, but all the ones which are missing, because I mean it's impossible to include all simulation techniques which have been published since the beginning of the time. So that's why we also see VirtualLab as a programming platform, so a high-level programming platform. So you can program sources, components, and detectors, and you can do this in C#, C++, or MATLAB. And the only thing you have to care about, the only restriction you have, is that as an input field, for example, for your component, you need an electromagnetic field. And as an output, again, you have to give back an electromagnetic field. And in between, you can do whatever you like. So I would like to show you this great flexibility by the simulation of a pulse focusing setup using an off-axis parabolic mirror. So we have a plane wave, which is illuminating some off-axis parabolic mirror, which is then focusing a beam here on a plane, an off-axis plane. So and I will just now load the setup which I've built up. So here you see our plane wave, and we go in a distance of 20 millimeter. And if you double click here on the optical interface sequence, here I've included a programmable interface to describe our off-axis parabola. So we can go here on edit, and we see now here that I have used an analytical formula describing the height profile. So you see an off-axis parabolic equation, and you can go here in 3D view and you see the curved parabolic surface. Then I have placed here behind, I have placed some silver there, and just some back surface of the mirror. And then I have placed a coordinate break to nicely position the screen off-axis, or the detector's off-axis, in a distance of 25.2 millimeters. And I will just show you now a ray tracing result to save some time. So, and I will just show you this for a monochromatic field. So you see we start here with a plane wave, go on the parabolic mirror, and then focus the light to an off-axis position. Of course, you also could do this now fully electromagnetic for a femtosecond pulse, and if you do so, again, you see here the 2D evaluation of the pulse. So you have here on the x-axis the time, and the position line gives you again a cut through the beam along the x-axis. And then you see here some diffraction effects here in the outer region, and you also see here in the inner region the shape of the spatio-temporal shape of the pulse. I would like to also show you another example, which is the pulse propagation through grating. So I will just build up this setup now again. So I will take a new light path diagram, and I will take again a Gaussian wave or Gaussian source, and I specify my pulse spectra, and it should be 10 femtoseconds long. And I load this into the source. And now I will place a sinusoidal grating in our optical setup. Here we have different opportunities, so we can simulate real gratings and idealized gratings. So the difference is that in an idealized grating, I do not have completely to know the exact structure. I just can assume, for example, I have a certain period, and I use some certain approximations to solve the problem of the light propagation through this grating. On the other hand, I also could simulate real grating, so I can really specify a very complicated stack of different interfaces, of grating interfaces, and some material in between. So I could really use the grating toolbox and do an rigorous Fourier modal method. It's a kind of Maxwell solver, and propagate the light through this. The reason why we have included this ideal gratings is the fact that most of our customers, if they buy a grating, the manufacturer of the grating does not tell you what kind of grating you really have. So they just tell you maybe the period and maybe the material, and that's it. But they don't tell you what is the structure, shape of your grating. So that's why I will now just use an idealized form, and I just now assume a sinusoidal grating, but I will not do really a rigorous analysis. And now again I will place an identity operator, and I will also place again a virtual screen, and I will place some pulse evaluation detector, and I combine all of these components and I specify the period of my grating, and it should be 15 micron, and we would like to end up with a modulation depth of 1 volt over meter. So that's what I mentioned with the idealized model. So we just have here not the real physical structure included. So it's just a transmission function we multiply there on top. To increase a little bit the resolution, I will increase a little bit the sampling so that we get a nice smooth picture. And I would like to be interested in the femtosecond pulse in a plane 10 millimeter behind the sinusoidal grating, and I also will now connect all of the detectors to the identity operator. And again, I would like to save some time, so I switch the simulation technique here between the sinusoidal grating and the identity operator to a rigorous angular spectrum of plane waves free space propagation operator. Now I just have to specify the our detector, and I would like to get again a 2D evaluation of the pulse along the optical axis, along the x-axis, sorry. And now we are already done, so I can just click now here OK, and I will start the simulation. And now VirtualLab will step by step propagate each harmonic field. You can also see it here in the logging. You will see here now. He always says free space propagation done. So this is for each harmonic field. He's propagating now the light from the axis of the grating to the identity operator over this 10 millimeter. And when we have propagated all of these harmonic fields, in the end, the inverse Fourier transformation is done and the virtual screen is evaluated, and we end up with the result which you can right now see here. So first of all, again, let's go to the identity operator, to the virtual screen. So you can clearly see here now nicely the 0th order, the minus first order, and the plus first order for all 29 harmonic fields. We can see here also the pulse length of the 0 order directly in the center. And what is more interesting, we can also now see here the pulse along the x-axis. So we have here the 0th order in the center, the minus first order, and the plus first order. So you can also clearly see here some pulse front tilt due to angular dispersion. So pulse front tilt means that here, if you're getting closer to the optical axis, the pulse of the minus of plus first order is coming earlier than here the outer regions of the pulse. If we're doing diffraction effects, then also coherence is very important. And here a classical example is a double slit experiment. So we take a 10 femtosecond pulse at a carrier frequency of 800 nanometer, and we propagate this pulse through this double slit, and then we use a 2F setup to match or to propagate light on a screen. And now there's the questions: what happens if I place here a thin glass plate in front of one of these slits? And if you don't have a glass plate in front, then the pulse which is propagating through the left slit and the one which is propagating through the right slit, they are interfering with each other, and you get a nice interference pattern. And if you go here again, evaluate the pulse along the x-axis, you see here again such kind of nice, some kind of nice shaped pulse distribution. And if you now add a 40 micron glass plate in front of one of these stacks, then there's a delay of the pulse which has to propagate through the glass plate. So the pulses, the second pulse appears in time shift with respect to the first one, which has propagated through the slit without the glass plate. So they cannot see each other anymore, so they are not interfering with each other, and then you would not see the interference pattern, and you would get such kind of double, let's say, call it a double pulse, where you have two pulses close to each other. Also a very interesting setup are pulse stretchers and compressors, which are of certain importance in the femtosecond community. So here I would like to show you the application scenario 548. You can also find this application scenario on our website. If you just in the download area type in pulse stretcher, or if you type in 548, you will find the application scenarios, and you can also find the corresponding VirtualLab files, which I will show you in a few seconds. So in this scenario, we will do the simulation of a grating stretcher and compressor for laser pulses. The first component is a grating stretcher and is used to stretch the femtosecond pulse, and afterwards we use the compressor to recompress the initial pulse, to recompress the pulse to get its initial pulse duration. As I already mentioned, in VirtualLab we have two options to simulate such kind of components. We can use idealized models and realistic models where we really know the geometrical structure. Again, here in this example, I will discuss the ideal pulse compressor and stretcher, because also here normally people don't know how their compressor looks like really, because they just buy one and the manufacturer does not tell you how it looks like. But obviously if you know the parameter and if you have everything, then you also can do a rigorous analysis of each of the gratings and do a more accurate simulation of your pulse stretcher and compressor. So here again you see you replace the C operator by this T operator, and this is an idealized operator which assumes that the effect is of the whole system, of the whole stretcher or compressor system, is just in a single plane, and it just affects has an effect on the frequency or on the time and not on the position. So, and our optical setup, which we have built up in VirtualLab, looks like the following. We have the Gaussian wave, and we have a stretcher, and we have the compressor, and always after each component we evaluate the pulse length, and the center position, the full width, have maximum is evaluated, and we will see how it is changing. The pulse stretcher has the following structure. It consists of two gratings and two mirrors, and as I mentioned, we just assume now this pulse stretcher set up by a transmission function we will simulate by an idealized transmission function. So that means that we will just introduce a phase shift which is obtained by the analysis of the optical path length here for the different frequencies, if the different frequencies are traveling here through the pulse stretcher, and you can give an analytical equation for this, and it looks in the following way. And we have realized this component by a programmable component, and we have introduced here all of the global parameters here which you can change and which are also available for parametric optimization. I will come to that later. In the same way, we have used we have realized the pulse compressor. It consists of two gratings and a mirror here, and again here you can do can write an analytical formula for the phase shift depending on the wavelength, which is introduced by this pulse compressor. And also now it turns out that if you choose the distance between the two gratings of the compressor to be equal to the grating constant times the tilting angle of the stretcher, then you can exactly recompress the pulse after the stretcher using the pulse compressor. So I will just show you very quickly now the simulation. So this file I've loaded now you can also find in the application scenario 548, and I will just start the simulation, and we start with a 10 femtosecond pulse, which you can see here, the pulse length. We go through the stretcher and we will end up with a stretch pulse of 921 femtoseconds, and after that it is recompressed again and we end up again by the initial pulse length. And you can also check again here the different temporal distributions in the time and frequency domain. For example, here we see it in the time domain, and here you see the spectra. You can also display here now the spectrum, and we can also watch the phase of the spectrum and not only the amplitude. And again, if you go here after the compressor, we have again a very short femtosecond pulse. So our last example we will discuss for today is the Gerard-Tourneur interferometer. So this can be used for the compensation of dispersion of long femtosecond pulses. So typically this is a setup which is used for femtosecond pulses which are larger than 100 femtoseconds. And we will see in VirtualLab how we simulate such kind of GTI interferometer for the compensation of dispersion for femtosecond pulses. And by this GTI we can produce desired positive but also negative group delay dispersions by varying the design parameter. And so the basic principle of such kind of GTI is it consists of a standing wave resonator, which has a partially transparent first interface and second high reflection interface, and they are separated by a certain thickness, and you have a certain angle of incidence where the pulse is coming in. So these are the degrees of freedom you have. Again, we use an idealized model, and if you do so, then we can write down the frequency-dependent phase shift of an idealized GTI is given by this formula, and also the second order dispersion, so the group delay dispersion, turns out to be a periodic function which is given by the following equation. That means that if we vary the gap between the mirrors or the incident angle or the reflectivity of the top mirror, we can tune the group delay dispersion of the GTI. And that now let's take a dispersion compensator setup. So that means that in VirtualLab I load the setup. So we start here now with a source which has already we start with a pulse which has been already stretched by the propagation through some dispersive BK7 glass, and now we try to recompress this pulse. And this GTI again was realized by some programmable components, and here you have again all the degrees of freedom you can evaluate. And I will now just start the simulation, and now you will see that we start with an pulse length of 366 femtoseconds. Here you see the GDD, which is introduced by the GTI. So here you see it again. This is the GDD. And you see that due to this inclusion of the GDD, you have compression of the pulse, and you end up with 240 femtoseconds. You can also see now that the pulse is slightly compressed, but however you also have here this kind of deformation of the pulse envelope, and if you multiply with the carrier frequency, you see the oscillation of the electromagnetic field. So during this webinar, mainly I have talked about the simulation of ultra-short pulse setups. Of course, you can use also VirtualLab for the optimization and tolerancing of such kind of setups, and therefore the simulation was the basic first step, because if you can do a simulation by field tracing, an iterative repetition of this field tracing approaches also now helps us to optimize and tolerance optical setups. That means that, for example, you start with a certain parameter set, propagate the pulse through the optical system, get the pulse distribution in the target or detector plane. From this, you can calculate an merit function, and from this merit function, a local or global optimization algorithm can deduce the changes which are necessary to get a better result of your optical system. And you can do this by local or global optimization algorithm, but you also could do a so-called parameter run, which allows you to do a simulation series. And this is the fundamental for position tilt and fabrication tolerancing, as well as for Monte Carlo simulations. I will just quickly show you this again by the GTI example, and I just will now vary the angle of incidence of the pulse in the GTI for tuning the GDD to see how the change of the angle of incidence is changing the outcoming pulse length. And I can do this. I will just go in the I will just switch off here some of the parameter. I will now just go here in the parameter run, and in the parameter run now I have access to all of the global parameters of the GTI. For example, I have here the thickness, and I also can change here the angle of incidence. And let's change now the angle of incidence from the 10 degree, which we had in our previous simulation, and let's go up to 17 degrees, and let's do this in 10 steps, so with an step increment of 0.77 degrees. And now I would really like to evaluate the pulse length after the GTI. And now you see here all of the different parameters which you have, and VirtualLab now will step by step do the simulation and calculates the resulting pulse length. If you do so, this will take approximately 2 to 3 minutes, but I will just skip this now. I will just show you the results. You will end up with such kind of curve. You will see, if you vary the angle alpha, you will see how the full width of half maximum pulse length will dramatically vary, and you will see that around 12 degrees we will have a shortest pulse, and around 14 degrees you will have a longer pulse, you will have a pulse stretching. So this is due to the fact that if you go from the minimum to the maximum, also you will tune the GDT from a negative region to a positive GDD, and that's why you get this pulse extension instead of the pulse stretch instead of the shortening of the pulse. So now in the last minute, I would like to show you some of our latest research results, which we have published recently with our friends from the University of Jena. So you can find the publication in the JOSA A issue, in the current JOSA A issue, so it was really published 1 week ago, and we have investigated the pulse front tilt in a simultaneous spatial and temporal focusing setup by VirtualLab. So the question was, or the simulation task was the following. We had an incoming pulse, and we splitted this incoming pulse by 2 gratings to really spatially separate the spectral components. And then we used a parabolic mirror or some kind of aspherical lens to focus this separated spectral components into the focal plane, or we brought them into the focal plane. And by this separation, first separation of the pulse, and then the focusing, we get a so-called spatial and temporal focusing. That means that by the separation of the spectral components, the bandwidth locally, of course, is smaller, and this directly results in a stretching of the pulse. So that means that here in the center region we have a longer pulse. And if we now overlap again all of the spectral components in the focal region, then the bandwidth again is increased and the pulse is shortened. So this is what the temporal focusing means. And spatial focusing is the obvious fact that we confine the beam in the focal plane, and so we make the beam diameter smaller just by this parabolic mirror. And main idea of this spatial and temporal focusing setups, they are very important, for example, for laser material processing, or if you would like to generate very high intensive pulses in a very short volume. And we have simulated the gratings by a rigorous Fourier modal method because we knew the structure of the gratings. We propagated the light by some rigorous free space propagation techniques, again used in FMM, free space propagation, and a geometrical optics operator for the simulation of the lenses or the mirror. And then we propagated again by free space propagation techniques the light in the focal plane. And here you see the pulse in front of the focusing mirror. That means that here we still have the separated spectral components. In the upper figure you see the SSTF setup. So in the x-axis you have here the times, the pulse length, and again here we evaluate this along the x-axis. And due to the separation of the spectral components, obviously the lateral extension of the light is larger than for a conventional non-SSTF setup where we don't have the separation of the spectral components. However, due to this separation of the components, our pulse also is stretched due to the reduction of the bandwidth. And here you also see it in a color mode. Here you see really clearly that we have separated spectral components, separated colors. And here in the lower region, the conventional focusing setup, we don't have this separation. So if you now evaluate again the pulse along an x-axis, and we now, for example, do a Fourier transformation, then we also can see here some tilt in the x omega domain. That means that different frequencies are located at different lateral or axial positions. And this is obviously just the case for the SFTF setup and not for the conventional one. So now what happens if we now focus these SSTF setup by an achromatic lens? For the conventional one, where we don't have a separation, you will just get a nice pulse front which is perpendicular to the optical axis. But for the SSTF setup, you always will end up with an pulse front tilt. That means that here the lower part of the pulse is arriving earlier than the upper part here. And this obviously you don't like in laser material processing. You would like to really have that at each position the pulse is approaching at the same time. And you can also see if you increase now the spectral separation, if you increase it, the tilt is becoming stronger and stronger. So this was one part of our investigation, and if you would like to learn more about this, I recommend really to read the paper. So in the end, I would like to come to my conclusion. So I hope you have seen that VirtualLab really enables the spatial-temporal simulation of ultra-short pulses, and it includes the angular and temporal dispersion effects, diffraction effects, coherence, polarization, and aberration effects. And by the field tracing concept, VirtualLab can simulate almost any source and optical components. And you can import this sources and optical components by catalogs, but you also can use VirtualLab as a programming platform and using MATLAB and C# programming to generate your own components. Also, the field tracing concept gives you, by its electromagnetic field representation, the access to any merit functions, and you can also program your merit functions, and you can then run local and global optimization as well as parameter runs for the optimization and tolerancing of ultrashort pulse setups. So this webinar video you also will find within the next days on our YouTube channel. There you can also find other interesting videos from former webinars, but also for some application scenarios. And you can get access to our YouTube channel via our website. Also, you can find nice application scenarios on our website, and you can also ask for a free trial version if you visit our website lighttrans.com. So I would like to thank you very much for your attention.